In this video, we will discuss normal distributions versus sampling distributions. We will talk about descriptions of each type of distribution, how to calculate the probabilities of each distribution, and how to differentiate between normal distributions and sampling distributions of the sample mean, and binomial distributions and sampling distributions of the sample proportion. First, let's talk about normal distributions. Normal distributions are bell-shaped. The majority of your data is in the center, and on the tails, your graph thins out. It approaches the x-axis but never crosses. The center of your graph is the mean, and the symbol that we use for that is mu. The spread or the width of your graph is called your standard deviation, and your symbol there is sigma. When our mean is equal to 0 and our standard deviation is 1, we call this our standard normal distribution. So let's see how your mean and your standard deviation affect what the normal distribution your graph is going to look like. Here we have a standard normal distribution because our mean is 0 and our standard deviation is 1. Your mean is the center of the graph. So if we change the value of the mean, this changes where the middle of your graph will be. Your graph switches left and right based upon that mean. Your standard deviation is your measure of dispersion, your measure of spread. So if your standard deviation is large, that means your values are more different than one another. So your graph is going to be wider, it's going to be flatter, it's going to be more spread out. If your standard deviation is small, that means the majority of your data are very similar to one another, so your graph is going to be skinny and taller and have a higher peak for that. Now let's look at our sampling distributions and first talk about the theory behind how sampling distributions are created. You have some population of individuals and you pick a sample size. Sample size is indicated by lowercase letter n. And you take every possible sample of that size from your population. And for every sample that you have, what we do is we calculate some sample statistic. So if you have a quantitative question, how many classes are you taking? How many children do you have? How much money do you have in your pocket? Then for every sample you take, you ask everybody in your sample that question and you calculate your sample mean for that x bar. So you have an x bar that's different for every single one of these samples, and we create a distribution based upon that. If you ask a binomial type question where there are two mutually exclusive options, a yes or a no, agree or don't agree, you vote, you don't vote, you're on time, you're not on time, then for every sample, what you're going to calculate is a sample proportion, which is indicated by the symbol p hat. Let's take a look at what that will look like. Here is our population. It is a normal distribution, and we select a sample size that we want. So we go to the population, we pull out two values, and we calculate a statistic for that. Here we're calculating the sample mean. And we do it again and again. And at the bottom, what you're seeing is we're building the sampling distribution of the sample mean. And the concept is you go to that population and you take as many samples of that sample size that you possibly can to create that sampling distribution. And we'll talk about the formulas in a second, but the central limit theorem is what tells us that the mean of your population is going to be fairly close, fairly equal to the mean of this sampling distribution. Our standard deviation of the population is always going to be wider, larger, bigger than the standard deviation of the sampling distribution. When you're taking these samples from the population, the majority of your data is in the center, so it makes sense that you're not going to pick lots of values on the ends. They're typically going to be in the middle, so the majority of your sample means are also going to be in the middle. Let's see what happens when we have a large sample size. Your standard deviation is even smaller. The graph is even more concise. So if your population would say something different, a uniform distribution, and your sample size is small, you see that your sampling distribution doesn't quite look bell-shaped. It looks more triangular here. But if we make our sample size larger, you notice that that sampling distribution now looks approximately normal. What if we started off with a distribution of proportions? You go to the population, you pick out all of your samples based on your sample size, and you ask a qualitative question, specifically a mutually exclusive question. There are only two answers that are available. So, yes being an answer will represent the one, no being an answer represents the two. So, you pick your sample size and you create your sampling distribution based upon that. But as you can see, that final distribution doesn't quite look nice. So what if we create a larger sample size? Now what does it look like? It looks approximately normal. So this will take us into our formulas that we're looking at. If you're dealing with sampling distributions of the sample mean, the shape of your distribution is going to be normal if one of these three conditions apply. So either if the population is normal, the problem that you're working with says specifically that the population is normal, then we can say that the sampling distribution of the sample mean is approximately normal. Or if your sample size is large enough, who cares what the original distribution is? Large enough depends on your textbook in your class. Our textbook says 30 is large enough. Other textbooks say 40, 45, some say 25. Or if you have the actual data, you create a normal probability plot, and if all of your data looks approximately linear and you don't have any outliers, you can use that as evidence to say that this distribution is approximately normal. Only one of these three has to apply. The mean of your sampling distribution of the sample mean, this is our symbol that we use, is equal to our population mean. And spread, the standard deviation of the sampling distribution of the sample mean, is equal to your standard deviation of the population divided by the square root of the sample size. We also call this value our standard error. Standard error. If you're dealing with the sample proportion, the shape of your distribution is approximately normal. If this is true, you multiply in your sample size times p, your population proportion, times 1 minus p, its complement. And if when you multiply these values together, the result is greater than or equal to 10, then we can say that the distribution is approximately normal. Some textbooks use N, P, and Q, Q being 1 minus P, the complement. Some multiply N times P and say that value has to be greater than or equal to 5, and multiply N times Q and that has to be greater than or equal to 5. Whereas the center of your graph, the mean of the sampling distribution of the sample proportion, P hat is the sample proportion, that's equal to P, your population proportion. And spread, standard error, is equal to the square root of P times 1 minus P divided by your sample size N. Next, how do we calculate probabilities? These are the techniques that you use to calculate a normal distribution. So if you're a calculator person, you are going under second and then vars, and you're choosing that second function normal CDF. So you go to second, vars, which is distributions, and you want normal CDF there. There you enter in your lower bound, that's the first argument, comma, upper bound, that's your largest second argument, then your mean, and then your standard deviation. You use this three different ways depending upon what area, what part of the graph you're trying to find the probability of. If you want to find the area to the left of a value, then your lower bound is negative infinity. And how we represent that is with the double E that's above the comma. If you use any other E on your calculator, you're going to get the incorrect answer. You could also put negative a million, negative 10,000. This just represents that you want the smallest possible value on the left. Then you enter your upper bound, the biggest possible number you can have, x. Then your mean and your standard deviation. What you're doing is you're giving your calculator a range of values that you want to calculate the probability under this curve for. If you wanted to find the area to the right, then your lower bound this time is the x value they're asking you about. Your upper bound, the biggest number you can have, is positive infinity. Once again, you can use 10 million, 5 million, just a very large number, 10,000. For some distributions, it could even be 100. Then enter your mean and standard deviation. If you're finding the area between 2 points, your lower bound is the value that's on the left, the smaller number. Your upper bound is the largest number, the number that's on the right. And then your mean, and then your standard deviation. If you're a stat crunch person, then you're going to stats, calculators, normal. You're entering your mean here, your standard deviation here. You only have two options, less than or equal to or greater than or equal to. For continuous distributions, you cannot find the probability of just one number. So that's why it's always either less than or equal to or greater than or equal to. This value is the z-score, or the random variable, the numbers at the bottom of this chart, at the bottom of the distribution. This is your probability, your area under the curve. This is your part in red. So you can use this both ways. If you wanted to find the probability of, or the area to the left of -1, you can do that. Or you can also say 25% of my data is to the left. What's the z-score that corresponds to that? If you're an Excel person, your function is norm.dist. And this is just like this first option with the calculator. You're finding the area to the left. If you want to find the area to the right, you still use this same setup, except now you find the area to the left and then you use the complement so that you can figure out what your area is on the right hand side. If you want to find the area between two numbers, you're going to have to use this function twice. So you first use it for x sub 1. That gives you the area to the left of x sub 1. Then you plug in x sub 2. That gives you the area to the left of there. And you subtract those two values just to find the area in between. If you wanted to find the probability for your sampling distributions, the setup is the exact same. The only thing that changes is that standard deviation, your standard error. So everywhere where you see it says sigma, if this is a sampling distribution of the sample mean, you will enter sigma divided by square root of your sample size. If this was a sampling distribution of the sample proportion, in this last spot, you would enter square root of p times 1 minus p. And then divide all of that by n. That's the only difference between normal distributions calculating the probability and then sampling distributions when you've said that your distribution is approximately normal. The only thing that you change is your standard deviation. You're going to now enter in the standard errors that you have instead of just the regular standard deviation. For proportion problems, you're going to enter P for your mean. How do you differentiate between these two problems? You have to slow down and read. That's what I tell my classes all the time. Slow down and read. We have become masters at skimming in statistics. You have to slow down and read carefully. A manufacturer produces 25-pound lifting weights, 26 pounds. The distribution is approximately normal. Here we have two different problems. Both of them ask similar things. They're both asking you to calculate probability, but you have to be able to read the problems and identify, is this a regular normal distribution problem? Because they said that the population is approximately normal. Or is this a sampling distribution problem? So here, find the probability that the mean actual weight for a sample of 100 weights is greater than 25.2. Here, find the probability that the weight is greater than 25.2. So because this problem asked us about the sample, this is a sampling distribution problem. Because it asked us about finding the sample, this is a sampling distribution problem. And this, find the probability that a weight is greater than 25.2, they're only asking you about one particular weight. So this is a normal distribution problem. We want to calculate the probabilities of both of those. Let's do this one first with the calculator just because it's easier. So where we want to go is under second and vars, which is our distributions. We want option number 2 for normal CDF. We enter in our lower bound, the smallest number that we want. Here you're looking for the area on the right. You want greater than 25.2. So our lower bound would be 25.2. Our upper bound, since we're on the right, is positive infinity. I'm using the double E99. My mean is whatever the mean of the population is. It says the manufacturer produces 25-pound lifting weights. And then my standard deviation is the spread. The lowest actual weight is 24, the highest is 26. So those are one value, 1 pound away from the mean. So there's my standard deviation. So the probability of picking a weight that is greater than 25.2, weighs more than that, is about 42%. So with our sampling distribution problem, you went to the population, you pulled out 100 weights, you calculated the mean for the 100 weights. Now for that sample, what's the probability that the sample has a mean of greater than 25.2? So everything is the exact same except for that very last term. Your standard deviation is the population standard deviation divided by the square root of your sample size, and our sample size is 100. So as you can see, that's a large difference from just talking about one individual weight to talking about a group of weights. Last but not least, let's look at a proportion problem. Approximately 60% of all part-time college students in the United States are female. So just seeing that percentage sign, we know it's a proportion. The first part says if random samples of size 100 were taken from the population of all part-time college students, what's the probability that 50% or less would be female? The other one says if 10 part-time college students in the United States are selected, what's the probability that 5 or less would be female? So both of these have proportions in them. We need to determine which one is a sampling distribution problem and which one is a binomial problem. So what we're going to do is use that first rule. N, sample size, times P, population proportion, times 1 minus P. If that value is greater than or equal to 10, then you're working with a sampling distribution of the sample proportion. So the first one is a sampling distribution of the sample proportion. The second one, our sample size is 10. When we multiply that by P and multiply that by its complement, you have 2.4. That's less than 10. So this distribution is not normal. So the second one will be a binomial distribution, and the first one would be your sampling distribution. So for the first one, since it's normal in our calculator, we're going to second and vars. We want normal CDF because we said the shape is approximately normal. We want 50% or less, so this time we're on the left side of a graph. So the lower bound, the smaller number, is negative infinity. You can absolutely enter in negative 10,000 if you like, or negative 100, just something that's very, very small. Then you enter in the value we're being asked about, 50%. Then you enter in the mean. The mean is your population proportion, so 0.6. And then you enter in your standard deviation. So this is the square root, and you see parentheses automatically pops up on mine, of P times 1 minus P divided by your sample size, 100. So 2% chance. In the second one, you have a binomial distribution. So you're still going under second and vars. Here you have two functions to select from. Binomial PDF is when you're finding the probability of one exact number. So if 10 part-time college students are selected, what's the probability that exactly 5 of them are selected? That's when you use binomial PDF. We want binomial CDF. Your C is for cumulative. You want to add all these options together. The arguments that you enter in how many people are you in study, 10. You enter in P, your probability of success, 0.6. You enter in the X value that they ask you about, and binomial CDF calculates the probability of this number and everything below it. So that will be 5. So 37% chance. I hope this video helped you to understand the differences and the similarities between normal and sampling distributions.